So, anyway, apologize for my voice a little bit. I got a little scratch, but I'm glad Mike talked before me. And we've had lots of ion outflow talks, so I can skip some of the introduction and just get right down to it. So I'm going to talk about coupling, mostly talk about coupling ionospheric outflow and magnetosphere models, and just the co-authors on this talk are Narutoshi Kitamura, who you guys have heard talk a couple of times. He helped me a lot on the data model comparisons that we did. And then also my colleagues at Goddard, John Dorelli and George Kosnoff, who I've worked with on parts of this work that I'm going to show you as well. So here I just listed some of the outflow mechanisms that people think are important, and I won't spend time going over them since you've all heard this, several times. But in this talk, I'm going to first talk about superthermal electrons on the polar wind. So I'm going to show some results that are, I think, complementary to what Mike showed. And then I want to talk a little bit about transverse heating wave-particle interactions. And here I'm not going to show you how to include that in the outflow model, but I want to talk about some of the shortcomings of our current approach of merging ionospheric outflow models with global models, and a potential pathway forward where we can make some progress. Oops, let me go back a second. All right, and so finally I want to talk about, I'm going to talk a little bit about reconnection in a quantitative way that you can evaluate the rate of reconnection in global MHD simulations, or multi-fluid MHD simulations. We actually developed, I think, a very robust method for doing this. All right. So I guess I can mostly skip this slide since Mike more or less showed it. But basically, there's different kinds of superthermal electrons, and we're focusing here on the photoelectrons for the case of ion outflow. And so this is a study I did mostly with Narutoshi. And so what I did is I modified the polar wind outflow model to include a kinetic treatment of photoelectrons. And so we simulated with this. We wanted to look at what's the background contribution during geomagnetically quiet times. We exclude the cusp regions and the auroral inputs. We're really trying to look at what's the contribution of the superthermal electrons to the quiet time solution. And so to do the comparison, we compare the model result. We had about 1,000 field lines distributed over the polar cap, and we compare our solution bin by solar zenith angle with Akabono satellite data that Narutoshi did an empirical fit to the electron density as a function of altitude and solar zenith angle. Also, again, some intercosmos satellite data and IceCat Svalbard radar data of electron and ion temperatures, both under sunlit and dark conditions. So this is the first result of that. So here I'm showing you on the vertical axis is radius. So one would be the surface of the Earth, and then here's the bottom of the FID and up to the top. And then the x-axis is the solar zenith angle, and the color contour is the log of the electron number density. And so on the left is the empirical fit to the Akabono data, and on the right is the what we reproduced with the model. And there's some differences, but in general, I think it's pretty similar solar zenith angle dependence and pretty similar result, which was encouraging. So the next thing we did is we did a comparison with the ion temperature and electron temperature under sunlit and dark conditions. So on the left, this is the sunlit, and on the right is the dark. And so this is altitude on the y-axis and temperature on the x-axis. So the model ion temperature is in green, and the IceCat Svalbard radar data for ion temperature is in blue. And you can see they show pretty similar growth, and they give pretty similar peak temperatures. In pink here, this is the electron temperature predicted by the model when we include the photoelectrons. And the black here is from the electron temperature data from the intercosmos satellites, and the red is the electron temperature from ESR. And in general, I think it's okay. The model does overpredict the electron temperature at the very highest altitudes, and it's underpredicting at the very lowest altitudes. I think this is probably due to a boundary condition. But in general, I think it does okay. Under dark conditions, all the temperatures go down, as you would expect. And so, but one thing I want to draw your attention to is we did this simulation with the photoelectrons, and we did it under two different conditions of topside electron heat flux. I mean, the topside electron heat flux is very ill-constrained parameter. And so we just used our, our standard value, and then we cut it in half, to see what the dependence is. And what you find is on the day-side, your solution's pretty much insensitive to your choice of electron heat flux, that the photoelectrons are really what's giving you everything. On the night side, of course, you don't have any photoelectrons. If you cut the topside electron heat flux, it makes a big difference in both the ion and electron temperatures as a function of altitude. So of course, all of this has impact for what's the composition as a function of altitude and solar zenith angle under these quiet time conditions. So what we did is we compared our results with some past studies, with study of Gordon Wilson in '97 and with George Kozanov's '97 paper. And so on the left, this is just the altitude profile of the log of the electron number density. The blue is our model, the black is the data, and this pink is from, or purple is from Kozanov's study, and the red is from Gordon Wilson's study. And we also looked, and the dashed lines are ones for the night side where you don't have a lot of photoelectron composition, and we include our night side result as well as the data and the result from Lemaire, which had very low photoelectron content. So we put that over here. And what you find is that there's a big contribution to the percentage of O plus as a function of altitude. So if you look at the percentage of O plus, you find that for the models that are that have low photoelectron content, the O plus drops off relatively rapidly with altitude. But on the other hand, if you have sizable photoelectron content, you can have O plus up to a very high altitude. But I want to emphasize that this isn't, just because you have O plus to very high altitude doesn't mean that you have large fluxes of O plus. A lot of this O plus isn't moving very fast. So even though the number density is high, the fluxes aren't necessarily high. It's kind of more of a long scale height. And this was just a nice study, a nice figure from George's paper where he just varied the percentage of photoelectron content at the base of his model from 0.01 to 1%, and then plotted a color contour of the O to H plus ratio. And basically, once you're above 0.1% of O plus at the base of your field line, you can have a very high percentage of O plus. So of course, Bob always likes to make the point that you really can't consider everything by itself, that you have to put a lot in. All I can say is that if you ignore the other mechanisms and just focus on this, it is very important. But of course, if you imagine that this is the background, suddenly you have a geomagnetic storm and a lot of wave heating kicks on, suddenly you have a lot of O plus available at high altitude from the beginning that you can accelerate out, and that'll interact and change things. All right. And so I'm not going to spend much time on this. I think Mike showed this picture. I just want to make the point that there's nothing particularly special about photoelectrons. Secondary electrons behave pretty much in the same way. If you have a lot of precipitation, right now in our global models, we use the precipitation to change the conductance, but it's actually, they should be more fully utilized, that you shouldn't just use them to change the conductance, but you could also use them to calculate secondary electron production and, include that in the outflow calculation. So I want to change gears a little bit and talk about what I think is a big hole in the existing paradigm for MI coupling right now. Right now, when we merge outflow models into into a magnetosphere model, we pretty much take density and velocity and temperature at the inner boundary and just let the magnetosphere model run with it and hope for the best. But Bob showed earlier in his talk that the distribution functions can be very non-Maxwellian, and we're going to take these and crash them down to a Maxwellian and expect good things. So there's some problems with that right from the beginning, but I want to show another problem. And that's, this was a nice study that Abdullah and Bob did in 2001. This is a field line convecting across the polar cap, undergoing wave-particle interactions in the cusp and in the polar cap and in the auroral region. And they did the simulation without any wave-particle interactions and with wave-particle interactions. And you see, of course, when you include the wave-particle interactions, you get a tremendous amount of transverse heating. But one thing I want to call your attention to is I drew a dashed line here on the bottom. And that dashed line represents the inner boundary of most magnetosphere models. And you notice that, at least in this case, a lot of that heating is happening not just in the outflow model. It's actually happening inside of, the domain of the magnetosphere. So you can't really use this paradigm that we're using now where you just expect the outflow model to handle all the wave-particle interactions and assume the magnetosphere model doesn't need to care about it. You really need to find some way to include this effect. And so at the very least, you have to extend MHD. And Bob talked about a very nice approach in the future of using fully kinetic models. But even with just sticking with the fluid approach, you can make some progress. You can't have the full complexity you could get from a kinetic model, but you can still make progress. So at the very least, we should consider moving to anisotropic MHD, or even better, multi-fluid anisotropic MHD. So this was a paper by Xing Meng, who recently graduated from Michigan, and she implemented the anisotropic MHD equations in BATS-RS. And there's some nice features of at least moving to this as a first step. And one is that you have a very nice term in the momentum equation that looks like the mirror force. Converts random perpendicular motion into organized parallel motion. And you could easily imagine adding a source term representing the heating due to the waves. And of course, it's not good enough if you don't know how to represent the wave heating. But but this isn't a problem that's unique to the magnetosphere model. If you're trying to do this in an outflow model, you're doing the same thing. And so right now, if you look at like what Bob and Abdullah do, they look at a lot of data and they try and come up with wave heating terms. So at least as a first approximation, we could do the same thing. So, what I did is I just looked at some of their papers and took the heating terms or the wave scattering terms that they came up with and integrated them into heating terms. And you could just apply those in the same way, at every point in your MHD simulation. So basically, though, now you need a new paradigm when you want to include this in your coupling. It's not enough just to set the density and velocity. Now, for each point in the magnetosphere, you have to set your wave heating term in a way that's consistent with the way you're setting it in your outflow model. So you have to make sure you're very consistent with that. So every point in the magnetosphere would have to trace back and figure out, am I on the cusp, am I on a polar cap, an auroral field line? What kind of field line am I, and what's the appropriate heating term to use? Now, there might be a better way to parameterize the heating term, but at least for this method, that's a way to go forward. And so in that case, if you're using consistent heating terms, at least you have some hope of at least capturing some of these effects in the global model. Certainly better than if you didn't include any pitch angle anisotropy at all. So, it's something we're still working on, but I can demonstrate, proof of concept that you can do this and it won't crash the code. So just to demonstrate that it can work, I set up an anisotropic MHD simulation and I moved the inner boundary down to about 6,000 kilometers altitude, where you expect some of the wave heating to be occurring. And I used relatively fine grid resolution, and I defined a region of wave heating over some altitude range. And I just put this wave heating term for the cusp, just the strongest term we have everywhere over the polar cap. And what you should expect is you should get very strong outflows everywhere. You should get very strong pitch angle anisotropy forming over the polar cap. And in fact, when we do the simulation, that's exactly what we see. Everywhere we define the wave heating term, we get very strong perpendicular distribution in the magnetosphere simulation. And if we look at the field line velocities, we get very strong acceleration and outflows. And this is, a contrived case. You obviously don't have such strong heating terms everywhere. But I want to demonstrate that you can make some progress in, a fluid type of approach. So finally, I want to change gears for the last time, and the last thing I want to talk about is calculating reconnection in global simulations, and a more quantitative way to do that. So this is a image. You're looking down on the Earth, and the sun is over to the right. And each of these dots is representing the junction of four topologies, where the open field line region meets the closed field line region meets the solar wind field line. So you have open connected to the north, meeting closed, meeting open connected to the south, meeting solar wind. And so this junction of four topologies is referred to typically as magnetic separator. We also identify the magnetic null points through using Green's algorithm, so we can find very accurately the location of the magnetic nulls. And if you think about how would you calculate the reconnection rate, once you know this, well, you can just integrate around here. You can use Faraday's law, and you know that the change of magnetic flux has to equal the path integral of V dot dl. And so just that E parallel integral around here can tell you the rate of change of flux. And you can then further divide that into the Dayside contribution and the night side. So you can do this integral between the nulls over here for the Dayside, and on the other side of the nulls for the night side. Or you could choose some other boundary, but I thought the nulls is a pretty reasonable boundary. So we've done this now for resistive MHD and multi-fluid MHD and Hall MHD and all sorts of things. And it's even applied this for full PIC simulations, local simulations. It works pretty well. So, here I want to focus on the effective outflow, since that's what I'm talking about, on the reconnection rate. And I want to focus on the Dayside. So I chose a grid using BATS-RS, and I really made a grid that's specifically to look at Dayside reconnection. So I made a paraboloid that wraps all around the magnetopause and provides uniform resolution of about 1/16 resolution over the entire current sheet on the Dayside. And it's important to do that because what we want to do is we want to try and minimize our numerical resistivity to be much smaller than the physical resistivity that we define. And the reason we want to do that is we want to know what the resistivity is so we can calculate the electric field. So anyway, once you do that, you can calculate all sorts of nice things. This is what it looks like in 3D. You can calculate your outer separatrix surface. It's the boundary between open and solar wind. You can calculate to very high accuracy the open-closed boundary. You can find your nulls. You can find a nice separator between them. And you can extract E parallel, J parallel, J along the separator with no problem. So then what we want to do is say, okay, well, let's look at, this is for, and one thing I want to emphasize, this is for a 135-degree clock angle. So this works for arbitrary clock angle. You don't have to have pure southward IMF and hope that your separator lies in a particular plane. So it's a very generalizable approach. So we wanted to say, okay, well, let's look at the effect of O+ on Dayside reconnection. So on the left, this is a single fluid solution with no specified outflow. And this is, we paint J parallel along the surfaces. And this is the multi-fluid case, where we use the exact same boundary condition as single fluid, except added another fluid on top, flowing out, pretty large amount of outflow over the whole polar cap. I'm just about done, so you don't have to get the hook out yet. So you can compare how does that magnetic separator look between the two. And if you look down from the top, you see that actually, so the pink is the single fluid case, and these are the nulls for the single fluid case. And these cubes are the nulls for the multi-fluid case, and the black is the separator for the multi-fluid case. And what you find is that in general, they overlap more or less where they are. And there's some difference if you look straight on, but looking from the top, the general position is pretty close. However, the nulls have moved Dayside in the multi-fluid case. Reasons I don't quite understand. These results are still a little preliminary. The other thing we find is even though, so the density is on the right here, and the electric field's on the left. Electric field is solid, and dashed is density. So even though the density is higher in the multi-fluid case compared to the single fluid case, we're finding that the reconnection electric field on the multi-fluid case is actually a little bit higher than in the single fluid case. So if you were to integrate that, you would actually have a higher reconnection rate, slightly higher anyway. So we're still working on that, trying to figure out what's going on. But in general, I do think this method is something that we should be going towards in global MHD to try and get more quantitative definition of reconnection when we're trying to see what the effects are in our models. So these are just the conclusions, and since Dan's standing up, I'm not going to reiterate them. I'll just let you fire away.
Really nice talk, thanks. I'll give the mic over here to...
A couple of comments regarding the last part of your talk, calculating the reconnection rate along the magnetic null. So what we found is that it's to distinguish Dayside and Nightside, it's better to look at the point where the electric field changes sign rather than just doing it on the non-decimal reading, because that way you capture all of what's happening, all of the flux that's coming in on the Dayside relative to the Nightside. It's kind of a minor point, but
No,
you know,
it's
when
well
you start to draw this out, it makes a difference. The other comment on transverse ion acceleration, I agree with you 100%. It's really a huge problem for us in the global modeling community to do this better. But the one thing I think that is crucially important in modeling transverse ion acceleration is what I like to call causal regulation. And so if we include transverse ion acceleration models that mainly are regional or kind of fixed or even indexed by KP or something like that, we're going to miss a lot of important physics. And I would like to just point out the work that Brambles did in finding sawtooth oscillations. That result would not have happened without causal regulation of the outflow, because there's a latency in when it's energized and when it impacts the magnetosphere.
No, that point is well taken. You know, a big shortcoming right now, and I'd like to say this isn't just a shortcoming for the approach I propose, but you know, in including wave-particle interactions, even just in the outflow model by itself, is you don't have right now, you know, a good way to specify what the wave heating is, you know, at any given time. You know, so, you know, this approach I laid out was just, you know, making the best we can with some kind of average quantities. But you're absolutely right that, you know, in order to make progress, we really need some way to causally specify, you know, what the wave heating should be. So I agree with you on that.
I think we agree on that.
Andy's been telling me the same thing for a while.
Yes,
now.
I know. This would get Andy Nagy off my back because he's been bugging me about this. So yeah, I'll support your proposal as best I can.
All right, that's good news.
But to get to this study that you've been doing here on reconnection, you have an adaptive grid and you have resistivity proportional to the current or something like this. Could you tell us how you do that?
Oh, so in this case, I'm just using, because I want to do the simplest case I can. So even though it's not right, I use just a uniform resistivity everywhere. But of course, we can do this with anomalous resistivity. It would work exactly the same way, except when you calculate the E parallel, now you would have to calculate eta based on the value of J. But that's certainly fine. And actually, my co-author on this, John Dorelli, has done that with OpenGGCM, and it works pretty well.
Just a dumb question from an experimentalist. I fully realize that V normal, B normal, and E parallel in MHD context should all give you identical reconnection rates. But just because we do it with real instruments, could I ask if you've ever tried with your code calculating the reconnection rate with all three, and whether or not they just lay on top of each other?
Using which again?
You could either, you need to, the electric field, your E parallel is coming from V normal and the transverse magnetic field that's being transported or convected into the X line.
So RE parallel comes because this separator line, is actually a magnetic field line. And so U cross B is exactly 0 on this line.
I was just asking if do you calculate your E from the magnetic field vector and from the velocity vector?
No. Well, so we calculate the electric field from the generalized Ohm's law, so U cross B plus A to J in this case. But the U cross B goes exactly to 0 on this line. We checked that.
Okay.
And so we just have the A to J contribution. So I guess the answer is yes.
It sounds like a yes. But with instruments, of course, we do get slightly different answers for each of them. So
There is one other approach we could use that we haven't tried yet. Since we calculate these separatrix surfaces to very high accuracy, we could calculate the flow of mass through them, right? And that should also give us the same rate. But we haven't done that, and my guess is there might be some difference because nothing ever works right.
Last question. Okay. I just want to really reiterate Bill Watko's point, but I'd really like to emphasize that and say that's the most outstanding problem I think that we face is how to determine where the waves grow, where they damp, which way they propagate between those regions, what the overall wave energy transport situation is. And it's a really tall order from a modeling point of view.
Maybe we could have a mission for that.
First step is to observe it, I think, yeah, right.